All right, so this is a quick review problem, which is our application problem as well. So what we're going to do is take this cube, place it at the bottom of the aquarium that is 1 meter deep, and we're going to calculate what the force on the top of this cube is. And so this is just like we did before when we tried to find the force at the bottom of that aquarium. But now we're going to look at just the cube itself. So let's start like we did before. This is 0, and the total depth is 1 meter. So what we need to do is find out what the depth here, and obviously it's not to scale, because if you did, it would just tiny little cube down there and you wouldn't be able to see it. So we got to exaggerate it. So what we need to do is find out what that depth is. Our force, we know, is pressure times area, right? And so it's our delta. Delta dA. And so we already know our delta, that's 9,800. And the reason I'm not putting an integral right now is because we don't need it. This is just one slice that we're looking at. So it literally is the force coming down straight here. It's not adding up different pressures. The pressure at this location is the same at every single point on that cube. So we just need the depth. And our depth here is, oh, we can't use 20 centimeters. Everything has to be in meters. So if we have centimeters, we've got to convert it. If you remember, King Henry died by drinking chocolate milk. Tell you what to do. Centi, we move it over to because it's 100th. So we get 0.2 meters. So if that's 0.2 meters, then we need to find out what it is from here to here. So we're going to just remove 0.2 from 1. So if you remove that, you would get 0.8. So our depth here is 0.8. Now, what is the area that we are applying that to? That's what we need to know now. So we have our pressure. Our delta D is our pressure. So our pressure there was 9,800 times 0.8. And now we need to apply that pressure to this area. Well, it's just 0.2 times 0.2. So the area is length times width, which is 0.2 times 0.2. So that would just be 0.2 squared. Now we can plug it in our calculator and find out what that is. So 9,800 times 0.8 times 0.2. Oops, forgot the parentheses. 0.2 power of 2, or square it, and we end up with 313.6 newtons. So again, make sure everything is in meters. We're good. And so this was a constant pressure right there, not a variable. The pressure here is the same at every single point on the top of that cube. So we can just take our pressure and multiply it by the area to calculate the force being applied to it. Now let's look at it on the side. So that was the other one we did. So we draw our shape again. That's 0. That's 1. And then now we have a rectangle there. So that's x. All right, we can even put 0.8 on there, which we're going to need. And so that's our x, right? And so it has a width of dx and then a length. What was our length here? Our length is 20 centimeters. So we do our force equals our delta dA. And so our d here is our depth. See, our depth is x. That's why we place the 0 here, so it's a nice clean x. So that would be a depth of 0.8. That would be a depth of 0.9, and that's a depth of 1. So as x goes down, it tells us our depth. So x is our depth, and our area is 20 dx. Let me erase my delta and make it look less like an 8. All right, so now our integral, where are we going to go from? So let's look at our Desmos. Here's our cube. See how little it was? Let's zoom in to our cube right there. All right, so this is just that one that we did. So now we're going to move that rectangle up and down it with an integral. So where's the lowest that we're going to go? It's at the bottom. So that's 1 meter. And where's the highest our rectangle is going to go? It's at the top of the cube, which was 0.8. So our x is going to move from 0.8 to 1. And then we use our delta, and then 20x dx, and we plug it in our calculator. And we get 35,280. Now, that's a lot more than that. So we're looking back here and go, oh, wait, We use centimeters. This is a common error, and so I wanted to make the error just to prove this to you. So you cannot use centimeters. Again, we need to use 0.2 meters. We did it well here because we're using 0.8 and 1. Those are in meters. It's perfect. But here, it's not 20 centimeters. It's 0.2 meters that we have to use. So this is not 20. It's 0.2. So if we go back here, it's just to divide by 100 is all we have to do to convert it back. But we're going to put it there anyways. And we end up with 352.8. That's much better. Newtons. So the force being applied to this wall is more than the force applied to the top. So these should still be fairly similar. Not fairly similar, but like not like before. It was like 35. What was that? 35,000. That's a lot. They should be. Think about it. So think about it this way. They both are the same area. That one is a 0.2 by 0.2. That's a 0.2 by 0.2. But the pressure at the top one is constant. So that right there is constant pressure. As we do this side, the pressure is actually increasing. So you can think of that tiny little sliver at the top as the same pressure as the top. But each sliver as you go down is going to increase in pressure, giving us more pressure all the way down, giving us a greater force. So the force as we move down the wall is increasing those little slivers. The force that we apply to each of those little slivers is increasing as we move down through the wall. So the pressure is going to be bigger. But they should still be reasonably the same with just a 20 centimeter cube. Sorry, not same, close. So if you don't convert the centimeters to meters, it's a good way to tell that you did not do that.